Hello students, let us get some insight of our fourth unit topic, concurrency control. Now what do you mean by a concurrency? Concurrency means whenever multiple processes appear to run simultaneously by using the CPU time in the interleaved fashion, that concept is called as a concurrency. Concurrency doesn't mean that the CPU executes all the processes at the same time. Actually, the CPU time is interleaved between the processes and they appear to run simultaneously or concurrently. Concurrency depends on the work environment as well, which is nothing but dependent on the type or nature of the operating system. So concurrency is in short whenever there are multiple processes and those multiple processes are executed by the operating system. Now there are different natures of the operating system. As we know, there is the multi-programming type of operating system in which there is a single processor or a uniprocessor system in which the multiple processes are executed. On the other hand, whenever there is a multi-processing system, there are multiple processors. As we know, we have the computers with quad core, octa core processors. Those type of operating systems are called as multi-processing operating system because they consist of the multiple processors. So if your multiple processors are managing or handling multiple processes, then it is called as a multi-processing operating system. Then there is one more concept called as distributed processing. In the distributed OS, it is the OS required in the field of distributed computing. Distributed computing has a lot of computers with separate memories and separate processors but working towards a collaborative task. So if the operating system is for the distributed computing, it is called as a distributed operating system. And if that operating system is managing the multiple processes which are executing on the distributed computing systems, then that operating system is called as a distributed processing OS. Okay. So concurrency simply means that if there are multiple processes, process is a small part of the program, and if there are multiple processes and all those processes want to share their context or want to upload their context in the primary memory at the same time, then that work environment is called as a concurrency, and the concurrency is handled by the operating system, the kernel of the operating system. That means the OS or the kernel is responsible for sharing the CPU time between different processes in a concurrent manner in a interleaved fashion. We know there are different types of algorithms for giving the CPU time to different processes. There is round robin algorithm, there is fastest job first or shortest job first, there is FCFS, first come first serve. So all these types are nothing but the CPU scheduling algorithms by which the CPU time is given to different processes in an interleaved fashion. Now there are certain key terms related to concurrency. There is a specific terminology which is used in the concurrency. Whenever the multiple processes are executed by the operating system, that concept is called as a concurrency, and there is a specific terminology for it like atomic operation, critical section of the code, mutual exclusion of the resources, rest condition of the processes, starvation of the process, deadlock of a process, and live lock of two processes. These are the different terms which are used in relation to concurrency in the operating system. Let us see the meanings of all these terms one by one. What is atomic operation? Atomic operation is simply the sequence of one or more executable statements that appear to be indivisible. That means in a process there will be a section of the code which will be indivisible, or it cannot be considered as a separate. All those statements will be considered as common statements, or they cannot be divided into different parts, and no other process can see an intermediate result of all those set of statements, or none of the process can interrupt the operation of those set of statements. Just imagine that your processor is executing certain instructions, for example, mul AB, div AB, and there is one atomic operation. That means there are 3-4 instructions which cannot be divided. Okay, all those instructions will work as a group of statements, as an atom which cannot be divided further. And whenever those group of statements are getting executed in the process, no other process can interrupt the process which is executing the atomic section or atomic operation of the code. Then the second term is a critical section of the code. Critical section of the code is again the group of statements, a section of the code which within a process which requires access to the shared resources. That means we know that multiple processes need different kinds of shared resources. Shared resources can be either the data structures, the memory, the file systems, or the IO or input and output devices of the computer. Suppose any of the process needs the printer. As soon as it gets the printer, then it enters into the critical section of the code. That means it is a code which is working on that particular resource of the printer, and as the process is working on the critical section of the code, no other process should be interrupting that process which is working in a critical section of the code. So critical section is a section of the code within the process that requires access to the shared resource and that must not be executed while another process is in a corresponding section of the code. So if one process is in the critical section of the code handling the printer, the other process should not enter into its critical section of the code in order to handle the printer. Then there is mutual exclusion of the shared resources. The shared resources, as I stated earlier, they can be some kind of memory data structure, or they can be some kinds of files. They can be the input and output devices like that. Okay, so or the CPU. All those resources are shared by different processes. What is a mutual exclusion? The mutual exclusion, the requirement that when one process is in critical section of the code that accesses the shared resource, no other process may be in the critical section of the code that accesses any of those shared resource. So it is very simple to understand the critical section of the code and mutual exclusion. These points are interrelated. Suppose process P1 is handling the printer. At the same time, process P2 also wants the same printer. At that time, the printer will be excluded. It will be exclusively given to the process P1 only. Unless and until the job of process P1 with the printer is done, the process P2 cannot have the printer. That means there is a mutual exclusion between the two processes P1 and P2 regarding the common printer. So shared resource, whenever one process is in its critical section of the code handling a specific kind of resource, at that time the other process cannot enter into the critical section of the code for that particular resource only. This is called as mutual exclusion of the shared resource. Then there is a race condition. A race condition is a situation in which multiple processes read and write a shared data item and the final result depends on relative timing of their execution. So in the race condition, there are again multiple processes. They are sharing some kind of data item. They are doing some read and write operation on that data item, and it depends on which process access that data item first, and depending on that the final result is dependent on the relative timing of execution of the processes on that particular data item. So let us try to elaborate the race condition by using this diagram. There are two processes P1 and P2 which are executing concurrently. Again, you have to understand that concurrently does not mean that the CPU is executing the processes P1 and P2 simultaneously. Of course, the CPU time is interleaved for the processes P1 and P2. At one time, only one process will be executed if there is a single processing environment. Of course, if there are multiple processors, then it is possible that the two processes or more processes will get executed depending on the number of CPUs in the system or processors in the system. Now, what is a race condition? There are two processes, P1 and P2. Process is a small part of the code, or it is a small part of the program, which is the executable part, which is independently executing. So P1 and P2 are the two processes executing concurrently. Both of the processes are sharing a common variable, or we can say it's a common resource, its variable name is count, and its initial value is 5. Process P1 tries to increment the value of count and process P2 tries to decrement the value of count. You can see here in a process P1 code there is count plus plus somewhere, and in P2's code there is count minus minus. These two are the processes. Now we cannot determine when this process P1 will be executed and when the CPU will be given to process P2. So that is completely depending on the CPU algorithm or the scheduling algorithm, which algorithm we are using. So we don't know at the user side which process will get executed, in which fashion or time occurrence of the process execution we are not aware of. So in this case what will happen is, for example, in this particular example it has been shown that the assembly language instructions for incrementing the value of count and the assembly language instructions for decrementing the value of the count variable. For example, the count has been moved into the register R0 in the P1 process. Then R0 register is simply incremented, and then from R0 that variable has been moved to its memory location, which is count. In P2 what is happening? The value of count is moved to R1. R1 is decremented, and again the value of R1 is moved to the variable count. Suppose the execution order of the instructions are, or the processes are, first of all the CPU is given to the process 1. So the first instruction of that P1 is executed, then the second instruction is executed for the P1, and then the third instruction, and completely the P2 process is executed. So try to understand that the CPU is given to P1, the P1 is executed, all the three instructions are getting executed in the P1, and the CPU is switched to the P2 process, and the remaining three instructions for the P2 process are executed. So what will happen in this case is, for P1 the value of count 5 will be moved to R0, it will be incremented by 1, and again it will be stored at the memory location where that count variable is earlier stored. So after that count is given to P2, it will be decremented by 1, so that the memory location count will have the value as 5 only. So final value of count will be 5. In the case 2, for example, what is happening is, if P2 process is getting executed, so that all of the instructions in the P2 process which are related to that count variable are getting executed completely, and then the context is switched to the P1 process, or the CPU is given to the P1 process, then what will happen is the P2 process will take that count variable into R1, it will decrement it, and again will store it in the same memory location. So the count will become 4, and the P1 process will again make it 5. So the final value of count will be 5 again. Let us see the third case, in which the CPU is given to the P1 and P2 processes in a different manner. Since CPU time is interleaved, or the CPU time is given to the processes in a bits slicing manner, we are not aware of the time slicing of the CPU which is given to the processes. Suppose in the case 3, the first instruction in a P1 is executed, then the first instruction in P2 is executed, and second instruction and third instruction of P2 is executed. So what will happen is, see, the first instruction of P1 is getting executed, then the P2, all three instructions are getting executed. So only the value of that count is moved to R0 for P1 process, and then the control is getting switched to P2 process. So the P2 process will get completed, and the value of that count will become 4 completely, and here that register is still having 5. Okay, so what is happening is, this particular count variable is moved into the R0 register. The R0 register is having the value as 5, and meanwhile the context is given to, or the CPU time is given to the P2 process. So the P2 process will have its context in the primary memory, it will get executed. What will happen is, it will get the CPU and all the three instructions of P2 will be executed. Meanwhile, the P1 process is restoring this value of 5 into R0. But in this case, since the P2 will get executed completely, it will change the value of 5 to 4 and it will be restored in the memory. But in this case, what will happen is, this 5 will get incremented by 1 and will become 6, and that will get restored in the memory. So for the third case in which the order of execution is only the first instruction of P1 is getting executed, then the P2 process all the three instructions are getting executed, and then the second and third instruction of P1 is getting executed. In this particular case, the final value of count will be 6. So what is our definition of the race condition? Race condition is a situation in which multiple processes read and write a shared data item or a shared variable, and the final value of that shared variable depends completely on the relative timing of the execution of the processes. How those processes handle that variable, their timings and relative timings decides the final value of the variable. This is the race condition. Now the meaning of starvation. A starvation is a situation in which a runnable process. A runnable process means a process which is able to run. This process is overlooked indefinitely by the scheduler. Although it is able to proceed, it is never chosen. That means it happens like our CPU scheduling algorithms are there. As I mentioned, there are various CPU scheduling algorithms, and there is a scheduler which is the main part of the kernel of the operating system, which will decide which process is to be selected and which process will get the CPU time. But many times, for example, our algorithm for the CPU scheduling is shortest job first or SJF algorithm. So in that case, what will happen is whatever is the process having the need of minimum time of execution will be served first by the CPU or served first by the scheduler, and that process will get the CPU time first. Okay, so the process which is requiring the smaller execution time will be first given the CPU, the other process will have to wait. In this case, what can happen is the process which requires the maximum time for execution may be overlooked indefinitely by the scheduler. Although it is able to proceed, it is never chosen, and then we say that that process is under starvation, it's not getting the CPU time. Okay, that is overlooked by the scheduler. Then there is a concept of deadlock. Deadlock is a situation in which two or more processes are unable to proceed because each is waiting for the other process to do something. So deadlock is, suppose one process requires a printer, okay, but at that time the other process P2 is busy with the printer. So the P2 process is having the printer, but it requires some IO device which is there with the P1 process. So P2 process is not able to proceed because it requires some IO device which is with P1, and P1 process is not able to proceed because it requires the printer which is there with the P2 process. So this type of situation is called as a deadlock. Deadlock can be better understood by this simple example. The real world example would be the traffic which is going only in one direction. Okay, for example, suppose the bridge is considered as a resource here. So what happens is this yellow car and pink car both are in a deadlock condition. So the resource is a single resource. Okay, so this particular resource is with one car, we can say, and the other car is indefinitely waiting for that resource. Okay, so this deadlock problem can be easily resolved if one car backs up. Then, so starvation is possible in the case of deadlock if one process continues to carry that particular resource which the other process wants, then in that case the starvation is possible for the process. The other kind of term which is related to concurrency is the live lock. Live lock is a situation in which two or more processes continuously change their state in response to change in other process without doing any useful work. So what is the difference between the deadlock and a live lock? In deadlock, both of the processes are in the waiting state. They are waiting for the resources which are there with the other process. So they are in the waiting state in a deadlock. In live lock, the two or more processes are in a running state. So that is the difference between the deadlock and the live lock. In the live lock also, it's a situation whenever there are two or more processes are locked, but they are simply changing their state in response to the other process, and they are just wasting time. They are not doing anything useful, but they are in a running state. That thing is called as a live lock. So that is different from the deadlock. For example, there is a process 1 and process 2, and both of the processes need some kind of resource. For example, process P1 is holding the resource which is R2, and process P2 is holding the resource R1, but P1 process requires R1 and P2 process requires R2. Only the thing is, both of the process are changing their states. They are not actually in a wait state. They are running, but they are changing their status so that the other process, according to the other process, they are changing the code inside them. So this is called as a live lock, which is different from the deadlock. Okay, so there are some design issues in the concurrency. Design issues means that concurrency is at the center of the operating system. We know that there are many tasks of the operating system. Memory management is there, CPU scheduling. Like that, there is a concurrency design. That means what are the design issues which are considered for the concurrency? Communication between different processes. If the CPU time is given to different processes, many processes need to communicate with each other. Now they can communicate by using a shared variable, or they can communicate by using the message passing technique. The message passing techniques in the processes are called as the mailboxes, the queues, etc. So those are the message passing techniques. Communication among the processes is called as inter-process communication, or IPC. Then the different processes can share the different kinds of resources, or they can make the competition among themselves for the resources. So different processes also compete among themselves for the different kinds of resources, and they can also share the resource in an interleaved fashion. Then synchronization of the processes. That means the time slicing of the CPU for the different processes, or there should be the timing synchronization between different processes. Then there is the allocation of the CPU time to the processes. This concept is called as CPU scheduling. So all these are the design issues in the concurrency. Processes has to communicate with each other, which is called as IPC, interprocess communication, either through the shared variable in the memory or through mailboxes, queues, that means by using the message passing technique. Then for the resources, the processes can compete or they can share the resource. There has to be the synchronization of the process. That means if we know that otherwise the race condition can occur. That means the P1 process should get executed completely, then the P2 process, then only the valid result of that particular shared variable is likely. So synchronization of the different processes, then allocation of the CPU time to the different processes. Okay, so all these are the design issues in the concurrency. The next points we will see in the next video. Thank you for watching this.